And welcome everyone to today's edition of Sun and Science. Sun is maybe lacking a little bit today, but to make up for this, we will provide you with some extra science. So today is the ninth session of Sun and Science. As you may know, Sun and Science is actually a part of our pretty well-known Soup and Science series of talks, which we usually schedule in September and January. So today we will have three amazing speakers lined up for you. I'll let you know who they are. So the first is Professor Daryl Haggard from the Department of Physics. That will be followed by Professor Anna Weinberg from the Department of Psychology. And lastly, we will have a talk by Professor Jonathan Sievers from the Department of Physics. So each of these professors will try to explain to you their research in about 5 minutes. After all three talks have completed, we will then put all of you into breakout rooms. So there will be 3 breakout rooms. You will be randomly assigned to one of those. And then one of the 3 professors will join that breakout room to answer any questions you may have. And after 10 minutes, another professor will be randomly switched into your breakout room. So in total, you will have a chance to ask questions to any of the 3 presenters. And after the end of all these 3 breakout room sessions, we will meet again here for some closing remarks. So I hope you will enjoy today's talks. And let's get started. First speaker will be Professor Daryl Haggard, again from the Department of Physics.
Hi, everybody. It's great to be here with you and to see you all today. Thanks for tuning in. So I'm going to be speaking today on behalf of my really fantastic research group, which contains around 10 to 12 postdocs, graduate students, and undergraduates. I work with all levels of different trainees here at McGill, and many of them work with me on this exciting work I'm going to be presenting today, which I have aptly named Black Hole Exotica. So I'm a member of the physics department, but also of the McGill Space Institute. And I study mostly supermassive black holes, but sometimes also lower mass black holes. Many of you have probably seen this really exquisite image. The first time we've been able to really peer right down toward what we call the event horizon of a supermassive black hole. This one is a black hole in a galaxy named M87. And if you're a bit of an astronomy buff, you might know it sits right down at the center of a cluster of thousands of galaxies called the Virgo cluster. So M87 is the first system we've been able to go in and look at the very, 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 very closest reaches near the supermassive black hole to see what's happening with the photons and the gas and the dust in this very, very extreme gravitational environment. So I want to start off by just describing a little bit what is a black hole. So there are a variety of different ways to describe a black hole. In many ways, they're some of the simplest objects in the universe. They're really primarily characterized by their mass, a little bit by their spin, and they can theoretically have a charge, but that charge in an astrophysical setting is neutralized so quickly that they very rarely carry any charge astrophysically. So here are a couple of definitions. So my favorite, most kind of tactile, easiest to understand description of a black hole is this notion of an escape velocity. So really, if you take any object and you make it very, very, very dense, even an object like our Earth has an escape velocity. So if you're Superman, you're sitting here on our Earth, and you try to throw a baseball, you'd have to throw that baseball at 11 kilometers per second. That's around 25,000 miles per hour, if you prefer those units, in order to get it into orbit around the Earth. So that's the escape velocity of the Earth. But now with a black hole, if you were to take the Earth and make it way more compact, or just add a lot of mass onto it, it turns out that escape velocity gets so high that it actually exceeds the speed of light. So light is just like your baseball. The photons themselves are trapped in orbit around the black hole, and they can't get out, and so we never see those photons. We never see that light coming from the black hole, hence the name black. So a black hole is basically just a very dense object with a very high escape velocity. couple of other descriptions. People often characterize these sources using a term called the event horizon. That's the sort of region within which photons are trapped. It doesn't really represent the size of the black hole so much, but it is the sort of visible sphere of influence of the black hole gravitationally. Often people also talk about singularities. This is a more mathematical notion. So you might think of a black hole as actually being a completely singular point in the fabric of space-time, a little bit like the idea of dividing by zero. So you basically end up with an infinity in the fabric of space-time, and we don't completely understand theoretically or certainly not observationally what happens down at that singularity. Is it truly a point? Is it an infinity? What happens? Do you get a wormhole, etc.? So these are some of the curvatures that are associated with different very dense objects. You can see even an object like our sun can slightly perturb space-time. A denser object like a white dwarf, the core of a star like our sun, might perturb it more, a neutron star even more, and a black hole really creates this extremely sharp discontinuity in the fabric of space-time, which is a different way of thinking about how black holes are interacting observationally. Okay, so I mentioned that if you wanted to make a black hole, you could actually make one with our Earth. So just take the mass of the Earth and simply squish it down to something the size of a sugar cube, and our Earth's escape velocity would actually exceed the speed of light, and we would be a black hole. So it has the same mass as the present-day Earth. It's just that it's way more compact. And so this is the thing that really characterizes black holes: very high masses and extremely compact geometries. So they are very, very, very tightly packed, very dense objects. So black holes come in sort of two different categories. I mentioned M87, the M87 supermassive black hole at the beginning. We have two different types that we talk about usually in astrophysics. One are stellar mass black holes. Those arise from the explosions of stars, from supernova explosions. And the other are supermassive black holes. Those are like the ones we've seen in M87. These sit down in the hearts of galaxies. So we have a supermassive black hole living here in our own galaxy, the Milky Way galaxy. Its nickname is Sagittarius A star, and it has around 4 million times the mass of our sun. So we use a lot of relative units in astronomy. We like to use solar masses because they're a little more intuitive. So you can see there are these two kind of categories of black holes: stellar mass, which are sort of tens to thousands of times the mass of our sun, and supermassive, which are millions to billions of times the mass of our sun. So we have a lot of different evidence. I mentioned we have this amazing supermassive black hole in our Milky Way galaxy. And in the Milky Way, we can actually see objects orbiting around that supermassive black hole. And we use basic Keplerian orbits to back out the mass of that black hole. And that's the most precise mass we have for a supermassive black hole. Though now this competing mass that we've gotten from the Event Horizon Telescope, which I'll talk about in just a second, for M87, is also very, very excellent from using general relativity and other constraints from that image. So this is the supermassive black hole here in our Milky Way galaxy. Moving on to that really amazing observation, which I started the talk off with. The Event Horizon Telescope is in fact not a single telescope, but a conglomeration of different telescopes that span the entire globe. So we use a whole bunch of different observatories, we link them together and correlate their signals to make that incredible image. So the Event Horizon Telescope made this beautiful discovery. This is really the first observational evidence we've had for that event horizon, that kind of point of last return for photons. And so this is our second. So we have the Keplerian orbits. Now we have this amazing image, and we have tons of other indirect evidence for black holes of all sorts of different masses. And so this is the type of work, both how do we understand the masses of black holes, and also how do we understand all the environment around the black holes. That's the work that we do here at my group at McGill. All of you are welcome to ask more questions, and I'll just leave us because, you know, science is governed by XKCD. Oh, sorry, I'll skip over this because I'm short on time, but I'll just say here's an XKCD comic showing you the size of our solar system overlaid on that amazing supermassive black hole image. So you can see our sun is down there right in the middle. You can see the orbit of Pluto, and Voyager, which is our spacecraft, which has gotten the furthest away from our own Earth that we launched here out there. So you can see this the entire extent of our human exploration with spacecraft fits roughly inside the sort of size of this supermassive black hole M87. And I'll leave it there.
Yeah, now our last speaker of the day will be Professor Jonathan Sievers of the Department of Physics.
Thank you. I'm very glad to go after Daryl because she's actually introduced some of the things that I want to talk about. So I get to hit bonus material. So I'm Jonathan Sievers. I'm a cosmologist, and cosmology is a study of the universe on the largest scales. So I work on a variety of projects with various group members. I'm going to tell you about one project that we're working on right now called HIRAX, and I want to try and set the stage for why we're doing this. So as Daryl introduced, you've probably all heard, sorry, I can't do a proper ball toss on Zoom, but what goes up must come down unless you throw it really hard. So if you threw your ball, as Daryl said, faster than the escape velocity, it wouldn't come back down anymore, it would leave. But the universe is kind of peculiar. So if you say there's a critical speed, so if you throw it right at the escape velocity, like it kind of doesn't turn around, but it also doesn't keep on going. But you have to hit that speed exactly right, because if you throw it a little bit slower than the escape velocity, it'll take a little bit longer, but the ball's going to turn around and fall back to Earth pretty quickly. And if you throw it a little bit faster, well, it's going to just keep on going. And so it turns out that's an exact analog for the universe. The Big Bang was a big explosion. Probably not coming as a surprise, it was a large explosion. And happened 13 billion years ago, 13.7. And if you ask yourself today, is the universe turning around or is it continuing to expand? Even today, 13 billion years later, it's right on the edge. And it's very hard to think that you could throw a ball up 13 billion years ago and come back today and have a really hard time knowing if the ball is going to turn around or whether it's going to keep on going, right? That's how finely balanced the universe is. And that almost certainly didn't happen by chance, because they're just incredible fine tuning. So the density had to be accurate to part in like 10 to the 50 or 10 to the 60 back when the universe was getting going for this to still be this close today. So that just isn't a coincidence. Now, if you ask yourself, okay, let me go look around and see what I see in the universe. Well, if you count up the ordinary matter, you see that it adds up only to about 4% of the critical density, right? So there's only about 4% of the stuff in protons, neutrons, and electrons that we see to provide the mass that we know it takes to balance the universe between expansion and contraction. Well, so for a long time, observers said, well, this is what you have. And theorists said, that doesn't make any sense, keep looking. So the observers went out and keep looking, and then sure enough, they found this dark matter stuff that seems to hold galaxies and clusters of galaxies together. And that turned out to be about 25 or 30% of what you need. So the theorists said, well, keep looking, you're not done. So the observers did, and finally, the Nobel result of the Nobel Prize about 10 years ago found conclusive evidence for what we call dark energy. So Einstein started this, and for what turned out to be bad reasons, but he ended up being right. You may have heard it called the cosmological constant. So what it is there's a background energy to space. You know, empty space is not actually empty. There's a little bit of energy there. And that acts like anti-gravity and drives expansion of the universe. That's great, because now observers have said, well, we think we see everything, and it agrees with the amount that the theorists said should have been there. So everybody's happy, except not quite. So if you look at the constants, just the fundamental constants of nature, you can combine them to get different numbers. And that usually sets the natural scale for what you expect to see in physics. So going back to Daryl, you can predict with how big do you think a black hole is going to be? Well, you've got the mass, and you've got Newton's constant of gravitation, and you have got the speed of light. And there's only one way to combine those to a distance. And if you say how big is a black hole, well, you would guess it's about that combination. And it turns out the exact answer is just a factor of 2 off. So you can combine, without understanding anything, you can combine constants of nature to make predictions, and those predictions are usually good to within a factor of a few. So you can do that for how much you think dark energy should be. You can take Planck's constant, the speed of light, and Newton's gravitational constant, and make a density out of that. And then we can compare that to what we actually observe in the universe. And it's off not by a factor of 2 or a factor of 10 or a factor of 100 even. It is off by 10 to the 122. So 122 orders of magnitude. Now, to give you an idea of how big that is, if you wanted to make a black hole, Daryl showed us you could take the Earth and squeeze it to the size of a sugar cube, and that would give you a black hole. If you wanted to match the density that physicists would predict for dark energy, you would have to take the mass, not of the Earth, but of the entire universe, and shrink it and shrink it and shrink it. So smaller than a galaxy, smaller than a star, smaller than a planet, smaller than a person, smaller than an atom, to actually about the size of a nucleus. So that's a really high density. And then what we observed is not all of the universe compressed to the size of a nucleus, but about the mass equivalent to 1 atom in every cubic meter. So it's enormously wrong. So you might then say, well, if the prediction is so wrong, then maybe the simplest model is just not right, and something completely different is going on. So that's what we'd like to test, is look at how the universe is expanded. You know, if you toss the ball up, how's the ball expanded as you look back in time? And that should be a signature. We can look at that, and we can tell ourselves, what is this dark energy stuff doing? Is it this very simple model, or is it doing something different? And there's no reason to think one way or the other. This is why we have to go observe it, because again, maybe the universe happened to pick just a really, really tiny coefficient, but maybe it's something completely different. So what we are doing is building a radio telescope to look at galaxies, and actually not even individual galaxies, but huge, very low resolution pictures of the universe. So this is from South Africa. It's a sort of a southern counterpart to the CHIME telescope, if any of you have heard of that. And what we're going to do is, over several billion years of the universe, look and see how the galaxies, the clumping of them, gets stretched as the universe expands, and that will tell us something about the nature of dark energy. So that's what we're going to do. Now the signal is very faint, so we need to build a lot of dishes to build up enough sensitivity to see the signal, because we're still looking halfway across the universe. So our hope is to build eventually 1,000. We're about to start the bids for the first quarter of this, and 1,000 6-meter diameter dishes. And so 6 meters, when you just talk about it in the abstract, sounds kind of small, but on the bottom left is an actual prototype dish that we've had custom built with a person for scale. So that's a 6-meter dish that we can build for a few $1,000s. And the surface is good to about a couple millimeters. So we're excited for that. So we're going to build this in South Africa, where the government has been very nice. And one of our big concerns is not being blinded by radio emission. So it turns out that a cell phone on the moon would be something like the 3rd brightest radio source in the sky. So if you try and build this next to people, all you're going to see is TV stations. So in fact, even though this is a very remote area, that was the case when we were getting going, but the South African government, because they're building the world's largest radio telescope here, actually has turned off TV stations where we are. And so it gives us a beautiful, clear view of the radio sky. So we'll start building this, well, with COVID now, it'll probably be next year instead of late this year. But there's lots to do. And you can see the bottom right corner is where the telescope will actually be built. And that's our little local resident aardvark hole. So lots of fun animals to go along with the science. So the project is called HIRAX, and it is named, inspired by these little critters that you can see in the top right, called rock hyraxes, or dassies in South Africa. And they live in the area, and they are actually most closely related to elephants. So you wouldn't guess it, but yeah, so we hope over the next few years to take data and to try and answer, is this dark energy stuff, is it the simplest model, or is it doing something different? Because we really don't know, and it's going to answer, we hope, sort of what the actual nature of space and time might be. So if you have questions, feel free to ask. Thanks very much.